Hi folks, the following video is our first one of the semester and it's on bonding. I'm going to be talking about Lewis structures and formal charge. Bonds are critical to how we think about organic molecules, and you want to think about bonds as what hold together the atoms in a molecule. We will mostly think about covalent bonds in organic chemistry, which involve two atoms that share a pair of electrons. We're going to focus on the valence electrons, which are the outermost shell of electrons for an atom. These are the ones that are used in bonding. And there's a trend you can see across the periodic table, which is that the number of valence electrons that an atom has increases going from left to right across the periodic table. So here's a small portion of the periodic table. Notice on the left-hand side, you have atoms like hydrogen and lithium, which each have one valence electron in their neutral state. Next is beryllium, which has two valence electrons. Going across the periodic table, moving to the right, we have boron with 3 valence electrons, carbon with 4, nitrogen with 5, oxygen with 6, and fluorine with 7. The octet rule is a convenient way to predict bonding for an atom, which is based on the observation that atoms tend to react in such a way and form bonds in such a way that they achieve a closed outer shell of 8 valence electrons. Below, I'm going to show some common bonding patterns for the most common organic elements and how they achieve their octets. We're going to think about hydrogen, carbon, nitrogen, oxygen, and the halogens, which I'm going to write as X. Here, this could be fluorine, chlorine, bromine, or iodine. I've arranged these in the order going from left to right that you'd see them on the periodic table. Hydrogen is our simplest case. It has one valence electron, and it tends to form one bond. It'll have 0 lone pairs typically. And the common bonding pattern to look out for is just to have a hydrogen with a bond to something else. Of course, it would be attached to some other atom here, but I'm not showing it. Carbon has 4 valence electrons, and to achieve an octet, it will form 4 bonds. A carbon with 4 bonds will have 0 lone pairs. To achieve a complete octet, nitrogen will use its 5 valence electrons to form 3 bonds and have 1 lone pair remaining on nitrogen. Oxygen has 6 valence electrons. To achieve an octet, it'll tend to form 2 bonds and have 2 remaining lone pairs. And the halogens, like fluorine, which already have 7 valence electrons, only need to form 1 bond to get a complete octet. This will leave the halogen with 3 lone pairs in addition to its 1 bond. So I want you to get used to seeing these patterns. Hydrogen having a single bond to another element, carbon making 4 bonds typically, nitrogen 3, oxygen 2, and halogens 1. The octet rule and thinking about how many bonds an atom typically forms is really helpful when drawing Lewis structures. In a Lewis structure, we'll use a line to represent a bond. We'll use dots to represent electrons. And you'll see that Lewis structures are a really useful way that we can predict how many bonds an atom has, how many lone pairs it has, and whether its bonds are single, double, or triple. I suggest using 4 rules to draw your Lewis structures. first count the valence electrons from all of the atoms that you're given in the molecular formula. Then connect your atoms with single bonds. Try to put the atoms that form more bonds toward the middle of the molecule, and atoms that form one bond to the outside. Next, you want to figure out how many electrons you've used in making your bonds, and then add the remaining electrons. These could be added either as lone pairs or by making double or triple bonds. And last, you'll need to assign formal charge. I'll describe later on in this video how to do so. So those were some rules to guide how you draw Lewis structures, but I also want to think about what are the goals when you're forming those Lewis structures. So your first priority, and the most important one, is to form complete octets whenever you're able to. Your next overall goal is to minimize formal charge. Third goal is to maximize the number of bonds in a molecule. And lowest priority, but still helpful if you're able to, is to put negative formal charge on electronegative atoms, if possible. Electronegativity is how well an atom pulls electrons toward itself. It increases going across the periodic table from left to right, as well as increases going from bottom to top. This gives us a diagonal trend where fluorine is the most electronegative atom. For example, if you had a fluorine in a molecule and you had to give it a negative or a positive formal charge, because it is such an electronegative atom, it would be better to give it a negative formal charge in your Lewis structure. To demonstrate how I would do this, I'm going to show you how I would draw the Lewis structure for H2NNH2. This is a molecule known as hydrazine, which is used in rocket fuel. The first thing I'll do is calculate the number of valence electrons in my overall molecule. Each nitrogen has 5 valence electrons, and there are 2 nitrogens in my molecule. So I'll have 10 valence electrons coming from my 2 nitrogens. Each hydrogen contributes 1 valence electron, and I have 4 hydrogens in my molecule. That gives me another 4 valence electrons. Overall, my hydrazine molecule has 14 valence electrons. Next, I'm going to connect my atoms together with bonds. Because nitrogen tends to form 3 bonds, I put them in the middle of the molecule, and then hydrogens, which tend to form only 1 bond, I put on the outside of the molecule. Now I want to check how many valence electrons I've used so far. Notice I have 5 covalent bonds, and each of those contains 2 electrons, so I've used 10 valence electrons so far. Because I started out with 14, I have 4 valence electrons remaining. I divided the 4 electrons between the 2 nitrogens as a lone pair on each of the nitrogens. Notice that each nitrogen has 8 electrons around it, and each hydrogen has 1 bond, which is its typical maximum. So I've succeeded in making my Lewis structure. Notice that this Lewis structure that I drew fits the bonding pattern that I mentioned earlier, that nitrogen tends to form 3 bonds and have 1 lone pair. I now want to bring up the concept of formal charge, which I mentioned earlier, which is a measure of the charge on an atom within a molecule. Most atoms in a molecule will have a 0 formal charge and nothing will be written, but sometimes you'll see an atom with a -1 or a +1 formal charge. How you calculate formal charge is you take the number of valence electrons of a free atom, and you subtract from that the number of electrons around the atom within the molecule that you're looking at. This number of electrons around the atom within a molecule is the number of lone pair electrons that it has and the number of bonds that it has. I'll demonstrate this calculation with 3 examples. The first example is NH3, ammonia. I want to start out by drawing my Lewis structure. I put nitrogen in the middle, the 3 hydrogens around it, and the nitrogen has a lone pair to complete its octet. To calculate nitrogen's formal charge, I need to first think about the number of valence electrons of my free atom, nitrogen. For nitrogen, this is always 5. Then I need to figure out how many electrons are around the nitrogen within the molecule. I need to think of my lone pair electrons. There are 2 of them. And then I need to think about how many electrons from bonds you can sort of think about belonging to nitrogen. You want to imagine dividing your covalent bonds in half. You can think about the nitrogen atom within this molecule as having one of the 2 electrons from each of the bonds. So overall, nitrogen in this NH3 molecule has 5 electrons around it. 2 from the lone pair of electrons, and then 3, 1 from each of the 3 bonds. Overall, the nitrogen of ammonia has a 0 formal charge. Typically, we wouldn't write this by the nitrogen. I'll show you how you would calculate formal charge for 2 more examples, both involving nitrogens and hydrogens. One of these is NH2-, and one is NH4+. For NH2-, to achieve a complete octet, the nitrogen will have 2 bonds to the hydrogens and 2 lone pairs. Notice that this immediately looks a little bit different from what we've seen before because the nitrogen doesn't have 3 bonds and a single lone pair. Now let's calculate the formal charge. The free atom of nitrogen will always have 5 valence electrons. I have 4 electrons from lone pairs around the nitrogen, and I have 2 electrons from the 2 bonds around the nitrogen in this molecule. Overall, I'm subtracting 6 from 5. From this, I calculate a -1 formal charge of nitrogen within this molecule. So I'm going to end by writing a negative by nitrogen. You could write this as -1, but it's most common to just do the negative sign in a circle. Now let's do the same thing for NH4+. When I try to draw my Lewis structure with complete octets, I end up with this molecule where I have nitrogen in the middle with 4 bonds to hydrogens. Notice here nitrogen has a complete octet. To calculate formal charge, I'm going to start out with my number of valence electrons for a free nitrogen. This is 5, as will always be the case for nitrogen. And from this, I'm going to subtract the number of electrons around the nitrogen in my molecule. This nitrogen has 4 bonds around it, so you can think about the nitrogen as having 4 electrons around it in the molecule. Subtracting 4 from 5 gives me a +1 formal charge. To end, I need to draw that next to the nitrogen in my molecule. You could write +1, but most commonly you would draw a positive sign in a circle to denote that the nitrogen has a +1 formal charge. The math that I just showed you for calculating formal charge will always work, but there's a faster way to do it once you get used to bonding patterns. The trick is to look for deviations from the usual bonding patterns. If an atom in a molecule has one more bond than expected, it will have a +1 formal charge. An example of this was the NH4+ molecule. Typically, nitrogen has 3 bonds in a molecule, but in NH4+ it had 4 bonds, so it would have a +1 formal charge. And likewise, if an atom has one fewer bond than it usually does, it'll have a -1 formal charge. This was the case in our NH2- molecule, where nitrogen had 2 bonds instead of the expected 3. One final thought is that how an organic molecule reacts and behaves depends on its specific structure. And the specific arrangement of the atoms within the molecule is critical. For example, let's say I told you that I had a molecule with the molecular formula C2H7N. This tells you about the atoms making up the molecule, but it doesn't tell you the exact structure of the molecule. And it turns out that for this molecular formula, there are different structures that are possible. These two structures are drawn below. You could either have carbon, nitrogen, carbon in the middle of your molecule, or carbon, carbon, nitrogen. Both of these molecules obey all of the octet rules and bonding patterns that I talked about, but they are different structures. We'll call the relationship between these two structures that have the same molecular formula, but a different connectivity of atoms, constitutional isomers. We'll see this concept of constitutional isomers many times throughout the course, so you want to start looking out for molecules that fit under this category. Alright, so in summary, today's video introduced bonding and Lewis structures. I showed you how to calculate formal charge and introduced the concept of constitutional isomers. That's it for this video. I'll see you in class.